Hello, everyone. I want to discuss section 10.1 on intermolecular forces. The learning objectives for this section describe the types of intermolecular forces possible between atoms or molecules in condensed phases. Those are dispersion forces, dipole-dipole attractions, and hydrogen bonding. Identify the types of intermolecular forces experienced by specific molecules based on their structures, and explain the relation between the intermolecular forces present within a substance and the temperatures associated with changes in its physical state. So let's go ahead and get started on this. We are going to continue with some of the ideas we were looking at in terms of the section, the module on gases, in that we are going to be thinking of molecules as these particles that are moving around. The difference here is that unlike with gases, we are now saying, well, they can also stick together. So gases, we were saying they only move around, they don't stick together. Well, now they do. And mathematically, that becomes very challenging. The good news is we are not going to do this mathematically. We're going to do this very qualitatively by discussing what can happen and how we can describe that, and maybe how we can perhaps talk about a hierarchy of a few of the things that can happen. So to start with, let's talk about some things that go on in solids or liquids. As we're saying right here, particles in a solid are held tightly together and usually in a regular pattern. In a liquid, they are very close together. The difference in the closeness of particles is not that much between a solid and a liquid. But in gases, they're very, very far apart. And there is no arrangement at all. For the solid, we have this tendency of the particles to essentially vibrate, but they basically stay in their same position. So they kind of vibrate around a little bit, but they don't really move around other than that. In a liquid, we can move around a bit more, move past each other, but they are still in contact with each other. While in the gas phase, they move around independent of each other, not touching each other at all. There are definitely some things in this picture that we haven't talked about yet, but for now we can see that we do have a regular arrangement for the solid, everyone in their place, whereas in the liquid we have this movement around, but they're still next to each other, and in the gas phase we have this movement where they are not next to each other at all. So there's actually, and I think I'll leave it here on this picture to describe this next idea, although it's discussed in the kind of this paragraph before the picture. And the idea here is that there are basically two competing forces. There's they're not forces in the terms of the Newton force, but two competing things going on here. We could describe some of them in terms of a force. We have the tendency to move around and the tendency to stick together, and they're basically in competition with each other. As we increase the temperature, we're increasing the tendency to move around, and that is within each of these. So within a solid, as you increase temperature, you have more movement in terms of there's more vibration going on. Same thing with the liquid, more movement of the particles as you increase the temperature. But we also go from solid to liquid by increasing temperature. We go from liquid to gas by increasing temperature. And of course, we already talked about that in the gas phase, we have increased movement as we increase the temperature. So that's one trend. As we increase temperature, we're increasing movement. Things are moving around more. The other trend is the tendency for things to stick together. So this increases with intermolecular force. So as the intermolecular forces get stronger, we have a tendency to go towards solid phase away from gas phase. Okay, so movement kinetic energy is temperature. Intermolecular forces is sticking together, leading to more condensed phases. So this section will be about identifying what are those intermolecular forces, what's causing that stickiness that molecules have that lead to them sometimes being something other than a gas. So let's talk about that a little bit. So we first want to understand that what's going on here is something between molecules. So we're saying forces between molecules. These are called intermolecular forces. So they're between different molecules. We also have the forces inside the molecule, the chemical bonds. So that's what we talked about in modules 7 and 8. Those are much stronger. Those are chemical bonds. So we might call those intramolecular forces, but we basically call those chemical bonds, right? Or covalent bonding. This is a different thing. This is between those molecules. So intermolecular force between molecules, and it's a much weaker type of interaction. The reason I'm saying this is that you want to understand when you're breaking these, you're not destroying a molecule, you're separating molecules from each other when you are breaking these intermolecular forces. These can all be clumped together in this term van der Waals forces, but there are three main ones that we'll be talking about. So the first are called the dispersion forces. Every molecule, everything that has electrons is going to have dispersion forces. So this is always true for everything. It turns out that there are some other things that certain things have, but everything has dispersion forces. And the idea here, and let's go ahead and look at this picture because it kind of illustrates it a little bit. Everything with electrons, remember those electrons are very random. They could be anywhere. So at a given instant in time, we might just so happen to have more electron density on one side of the molecule than on the other side. Now, there's not a reason why. Why is it here the right instead of the left? No reason, just kind of randomly, because the electrons are moving, and so it won't always be exactly equal. Because of that, what can happen is you also have another molecule that's doing the same thing, and whatever kind of that random instantaneous changes over here matches up with the opposite kind of random instantaneous change on the next molecule over. You'll notice we're indicating these with these funny symbols that look kind of like music notes. This is the lowercase delta. So we've talked about uppercase delta for things like temperature change. Lowercase delta here we're using to represent something also kind of small. And so it's basically some number between 0 and 1. So it's not a +1 charge or a -1 charge. It's somewhere in between that is what we're saying here. And we're not putting an exact number on it. It's just somewhere in between. These are temporary dipoles. So dipole being that you have this kind of difference in charge. So they're temporary. And we can also say that they are sometimes induced. And what that means is that because you have a partial charge here, that might lead the one next to it to also have a partial charge. So this is a very weak attractive force. But if it's all there is, then it can be meaningful. So again, the reason for this is because of electrons. So the more electrons you have, the more this is going to matter, and especially as you get farther away from the nucleus. So the trend that we see here is that the more you have, the more they matter. And we can see that here looking at the halogens, and we can see that both the melting point and the boiling point will increase as we increase the molar mass. Now, it's not because they're heavier, it's because they have more electrons. And and molar mass will kind of trend together. Number of electrons will trend with molar mass. So as you increase the molar mass, you will increase the melting point and the boiling point for things that have dispersion forces, which is everything, right? So we will always have that trend. One way of describing this is polarizability. So the more electrons you have, the easier it is to cause something that would not normally be polar to become polar, as we're showing here. Here we're seeing some molecules, and you can see this trend. I guess this is one you should be kind of practicing, so I won't say too much more about that. Okay, this next section we can kind of skip over. This is getting into a little bit more, kind of more detail on, well, what other things might make them stick together. So the shape of something might matter. I'm not going to care that you remember that aspect. But there is an interesting kind of application here of that related to geckos and their feet. Okay, I want to move on to the next type of intermolecular force, which are the dipole-dipole attractions. Now the picture here might look very similar to the one we just saw, but there is a difference. The difference here is that we have polar molecules here. We're talking here about polar molecules. So when we were, if you think back to Module 8, we were just determining if molecules were polar or nonpolar. The reason that matters is because it will determine whether or not we have these dipole-dipole attractions. Polar molecules do, nonpolar molecules don't. So the difference here between these pictures and the ones we had earlier, they look exactly the same, don't they? But the difference is that this one is always a partial negative, this one is always a partial positive. So it's not random, it's not temporary, it's always this way. So this attraction is going to be much stronger because it's always there. It's not just there kind of randomly. So things that have things that are polar molecules will have higher melting points and higher boiling points than things that are nonpolar, and that this is the reason for that. Okay, so there's a bit of a discussion in here related to that, and an example you can look at. Okay, the last of these intermolecular forces is called hydrogen bonding. This is a type of dipole-dipole attraction that is very strong, and there's a reason for that. So here we're showing water molecules as an example of something that does hydrogen bonding. And what's going on here is that if you think about the covalent bond that you have with hydrogen, you're sharing the one electron of hydrogen with another atom. So hydrogen is sharing its one electron. So that's the starting point. If that other atom is very electronegative, that sharing could be such that the hydrogen doesn't really have much of the electron. It's more on the side of the other atom. And so what you end up with when hydrogen is sharing its one electron and doesn't really have it very much at all, it's basically a proton. And so because you have this kind of full positive charge, you can get very close to that with something else that is very electronegative. So this can be a very strong bond comparatively, because you almost have a full positive charge here with something that's very electronegative. So for this to work, it has to be with something that has a very high electronegativity. And there's only a few things that do that. Your book talks about those here, so I will go ahead and highlight that. Those are fluorine, oxygen, and nitrogen atoms. So fluorine, oxygen, and nitrogen that are connected to hydrogen will have hydrogen bonding. Okay, it's not just any time you have hydrogen, it has to be one of these three elements that are bonded to the hydrogen for that to happen. I wanted to talk a little bit about why do we care about this? Why is this one so special? If you look at this trend, we can see. So these are the trends of group 15, 16, and 17 hydrides. So where you have the nonmetal bonded to hydrogen, and you can see kind of a trend here. And you can kind of guess, well, okay, so if we have the period 2 element in here, which would be those oxygen, nitrogen, and fluorine, where would you expect that to be in terms of the boiling points? It turns out they are not at all where you would expect them to be. They are a lot higher, extremely higher than the expected trend. This is because of hydrogen bonding. So this graphic is often used to show why hydrogen bonding is so important. So much more important, I shouldn't say important, much stronger than what you have for these others, which is going to be still a dipole-dipole attraction, but not as strong as hydrogen bonding. One last thing here I want to mention, there's some examples in here you can look at as well, is that DNA is a place where hydrogen bonding is happening. So in DNA, we're not going to get into this too much, but the kind of the double helix structure in DNA is held together by hydrogen bonds in here. If you didn't have hydrogen bonds, the DNA would not stick together. If it was only a dipole-dipole, it would not stick together. So you need the hydrogen bonds for that to stick together. But if it were say covalent bonds, it would be too strong and it would not come apart. Again, with DNA, in this, some of you may or may not be in biology yet, or may not ever take biology. But one of the things DNA has to be able to do is basically unzip itself. So it comes apart and then comes back together. And in order to do that, you essentially need to have hydrogen bonding. Okay? So that's one way in which hydrogen bonding is very important. So that is it for this video. So you want to be aware of the 3 types of intermolecular forces that we discussed here, and be able to rank molecules in terms of the strength of those intermolecular forces, and we see that with things like melting or boiling points.